When we look at linear equations, it's not only important to know how to solve for the slope and y-intercept, it's also important to understand what happens when we change the slope or when we change the y-intercept. That's when the linear equation becomes really powerful. In this video, we're going to look at what happens when those two parameters change. Then we'll also look at what we can say when we compare two linear equations just by comparing the slopes and y-intercepts. So remember, the slope is rise over run, or delta y over delta x, and the y-intercept is the point, the y value when the line crosses the y-axis, or when x is equal to 0. So let's take a look at some of these concepts. So let's first take a look at the effects of changing the slope m. We'll start by looking at a simplified line, the line right on top of the x-axis. This line crosses the origin, so it has a y-intercept of 0. It has a slope of 0 as well, because the rise at any 2 points on this line is equal to 0. And the run doesn't matter because it's just along the x-axis, right? So y is just equal to 0 in this case. So this red line represents a slope of 0. What happens when the slope is equal to 1? When the slope is equal to 1, we get y is equal to 1 times x, and then let's also keep the y-intercept 0 to be to have a direct comparison point. So then y is equal to x has a slope of 1. So a positive slope of 1, you see this rising, this line growing in the x direction, right? If x is equal to 4, y is equal to 4. We know this line. What happens when the line is vertical? When the line is vertical, that's a slope of infinity. So we wouldn't use the traditional linear equation to represent this line. We'd use x is equal to 0. And then if the line goes across in this direction, that would be a slope of -1. So this gives us good reference points. The closer we get to a line lined up with the x-axis, the closer we are to a slope of 0, either from the positive one side or the negative one side. And as we get closer and closer to the y-axis, the vertical axis, we get closer and closer to a slope of infinity. So we'll take a look at a couple more graphs to kind of fill in these missing sections here, but this will give you a good sense of the shape of your graph just by looking at the slope and see if it's positive or negative, and then how close you are to either 0, 1, or infinity, or a very large number. You can think of it that way. Okay, so to fill in the gaps, let's start with just the slope of +1, right? Remember, my x-axis is a slope of 0, and my y-axis is a slope of infinity. So if I choose a slope of 3/4, that's what my line would look like. I go rise 3, 1, 2, 3, go to the right 4, 1, 2, 3, 4, and you see that point is intersected here. Here we're still looking at the origin, or the 0 point, as my y-intercept. So we can consistently just, basically you can think of it as taking a ruler, holding it at the center and just rotating it and seeing, right? So this could be represent the vertical line. That would be a slope of infinity. This will be a horizontal line that's representing a slope of 0, somewhere at 45-degree angle, a slope of 1, and it's everything in between those. Here we have a slope of 1/2, then a slope of 1/4. Then we can fill in these missing gaps. This is representing a slope of 1, y equals x is representing a slope of 1. Here's a slope of 2, and here's a slope of 4. And a slope of 10. So you can see how the changing the slope affects the shape of your graph. But remembering the bounds of infinity, 0, and 1 will help you a lot. So next we can take a look at what this represents on the negative side. So remember, this is quadrant 1, this is quadrant 3. We can take a look at the negative slopes and represent it in quadrant 2 and quadrant 4. So just like we saw for the positive slopes, we have the similar behavior for negative slopes. So here's the -1 slope, or y equals -x. Here's -3/4, -1/2, -1 1/4, and then we can go towards infinity, -2x, -4x, and -10x. So we've changed our slope, and we could see how the line rotates about the origin because we chose that as our y-intercept point. What happens if I keep the slope constant and change the y-intercept? Well, in this case, all you're going to have are offsets, right? We're going to have parallel lines because it's going to be the same slope, and we're just going to offset it. So here we have a slope of 1 and a y-intercept of 0. Here we still have a slope of 1 in this green line, but our y-intercept is -2. And we can look at our y-axis to see that intersects at -2. So at every single x location, these two lines are parallel and just offset by a value of 2. Here's the same thing at x -4, so a y-intercept of -4, and then a y-intercept of -6 and -8. So you can see that all these lines are parallel. We know they're going to be parallel because the slopes are equal to 1. Then you have just more y-intercepts. Y-intercept of 2, y-intercept of 4, y-intercept of 6, and y-intercept of 8. So the key thing is if the slopes are the same of 2 or multiple linear equations, you know that those lines are parallel. If the y-intercepts are shifted, you know, are different, then you know that those lines are shifted by the difference in those y-intercepts. For example, this blue, let's say this line and this line. So here we have x + 4 and x + 2. The y-intercepts have a difference of 2. So these two lines will be offset by 2. And so it's a really easy way to identify how two lines will be different at any given x location if they have the same slope. So here I have 5 conceptual problems for us to think about, right? So each of these has 2 equations, and the equations have something in common, whether it be the slope or the y-intercept or something along those lines. And so I want you to think about at some value of x, right? How would you determine whether the y value of equation 1 would be larger or smaller than that of its corresponding equation 2? So I'll go through each of these 5, but pause this video now and take a look at this. Without actually plugging in values, can you make a general hypothesis, let's say? And then I'll show you the graphs of these, the 2 equations, and then what concepts we can think about when we are recognizing that they have common slopes or common y-intercepts. So take a look at this problem. We have y equals 1/2 x + 10 and y equals 3/4 x + 10. And we're asked which equation will be, which y value will be larger or smaller when x is equal to 100. So a positive x value. So what do you recognize to be the same? In these 2 equations, you have the same y-intercept, which means these 2 lines will intersect at the y-intercept. Then you look at these 2 slopes, and you recognize that equation 2 has a larger slope. So if they intersect at the y-axis, that means they have a common point there. Then if this one has a larger slope, it's going to grow faster than equation 1 will. So let's take a look at the graph. So this blue line represents equation 2 with a larger slope, and you can see that it's growing larger. So at x equals 100, it has a larger value. Because these lines intersect at smaller values than when they intersect, the opposite is true, right? So for negative x values, the red, or the equation 1 with the smaller slope, is larger. For positive values, the larger slope. So it's really important to know when they intersect. And so that's what we'll look in the future video. But we made it very easy for us in this problem set because we have the common y-intercept. So it's a very, very important thing to recognize here. What about this problem? Let's say we want to compare some x equals 10, right? So I arbitrarily picked this value. What's common between equation 1 and equation 2? Well, we have the same slope. So the only thing that differs is our y-intercept. So remember earlier I said that if we have a same slope, we have parallel lines. So if we have parallel lines and we're just offset, which one do you think will be larger when x equals 10? Well, we could take a look at our graph. Here's x equals 10. This shows us that the blue line, or equation 2, which has the larger y-intercept, is going to give us larger value. Well, that makes sense because if it's parallel, they're never going to intersect. If it has a larger y-intercept, that means at x equals 0, the equation 2 is going to have a larger y value, and so they're offset throughout the for all x values by this value. How much are they offset by? Well, 6 minus 3, they're offset by a value of 3 at any x location. So equation 2 would have a larger value at x equals 10. This problem looks similar to the one we just looked at, right? We have a different value at x equals 1 that we're going to compare. And what's common between these two equations? Well, the slope is common. Well, the slope is common, but this time it's a negative value. Does that matter? Well, we'll find out in a second. We have different y-intercepts, right? Which y-intercept is larger? Negative 2 is larger than negative 5. So equation 1's y-intercept is larger. What do you think that tells you about what the value at x equals 1 will be? Well, regardless if the slope is positive or negative, the fact that the slopes are the same means that these lines are going to be parallel, not intersect. So what we say earlier is that if they are parallel, whichever y-intercept is larger will always have a larger value. So let's take a look at the graph and see if that's true. So here we have equation 1, and here we have equation 2. Equation 1 here at the y-axis shows the larger y-intercept, and at some point 1 here you can see that it makes sense that the offset will remain and the equation 1 will be larger than equation 2. And this problem is similar to problem 1 that we looked at, right? So we have y equals negative x plus 2, and then y equals negative 4x plus 2. We have the same y-intercepts, but different slopes. In this case, the slopes are negative. Let's see if this plays a role. Common y-intercepts represent what? Common y-intercepts means that the lines intersect at the y-axis. So you have a common point there. So then at that point, you could just compare the slopes. So even though that they're negative values, you can compare which slope is larger, and you can determine which one is going to be larger or smaller, whether it's depending on if it's before or after the intersection or the intersect. So here's the blue line with a larger negative slope, and here's the red line with a smaller negative slope, right? So you have to be careful sometimes whether it's you're looking at the value, right? Are you comparing 4 and 1, or are you comparing the value negative 1 and negative 4? So after they intercept, the blue line is declining at a faster rate. So this negative value continues to decrease faster. So the red line, the negative 1 value, is going to have a larger value at x equals 10. After, right, that's true for after the intersection point. Before it, the opposite is true, right? So even having just some of this common understanding of how negative slopes, intersecting points affect things, and how parallel lines affect things is very, very useful. And finally, I have a y equals 4 and x equals 4. This is kind of a trick question, or just to kind of help us remember y. If y is equal to a constant, that means it's a horizontal line. If x equals a constant, that's a vertical line. So in this case, at any x location, you don't really make a comparison because there's no real comparison to be made when you're comparing slope of 0 and the slope of infinity lines. So hopefully these example problems give you a sense of what to look for when you have multiple lines, linear equations, and you're trying to make an assessment of how they affect each other. Now, these right now just look like math equations. What we'll see in future videos is where those applications could come from. It can come from a financial perspective. The slope could represent an interest rate, and the y-intercept a principal. And then in that case, it'll be very important to you to see the effects of different interest rate loans that you might take, or growth if you're investing, right? They can be looking at temperature, ramp rates of systems. And depending on what your objective is, you can use a lot of these lines to help you understand, or a lot of this assessment of, like, is it a larger or smaller slope? Is it a larger or smaller y-intercept? And are we looking at a case before or after the lines intersect, or do the lines ever intersect? So in future videos, we'll look at more of those concepts in an application basis.